Log on, tune in, find out. Another good idea from Cambridge.
Schwichtenberg, talk from Proofs and Computations.
Thank you. First of all, I'd like to thank the British taxpayer for installing this institute and also the organizers for letting me participate in this great event with so many interesting people to meet. Well, my talk is a very short one and it's not very substantial. It just tried to give you an idea of what I'm working on. So it's Proof and Computations, and there's a recent book together with my friend Stan Weiner, who's sitting here, with the very same title, and much of what I'm talking about can be read in more detail in that book. Now, I first want to motivate a certain line of research that I found myself engaged with recently, and this is about formalization of mathematics, constructive mathematics, and also extraction of computational content from such formalized proofs. Well, the setting is quite well known. From a constructive proof of a formula with some computational content, say for all exists A, one can extract a term which realizes, in a certain sense designed by Clini and Kreisel and Trulster, this formula. Well, why should we do that? Why should we bother about extracting things from constructive proof? Well, first of all, it can be quite important to know for sure, and also to be able to machine check, that you have a complete proof, that you didn't overlook something. That's the old question of correctness of proofs. Another point is, well, if this proof contains an algorithm, as a mathematician, of course, you see what this algorithm will be, then even if this proof is correct, when you later implement that algorithm, you may produce more errors so that this thing doesn't run. And even if this algorithm is correctly implemented, then for sensitive applications, it may well be that customers require a formal proof that the code implementing the algorithm is indeed correct. And I think that's quite an important application of logic these days, that these demands can indeed be satisfied. Now, what are consequences of this setup? Well, first of all, when you have a proof, then its computational content should not only be seen by the author of the proof, but it should be machine extracted from a formalization of this proof. So you need a fully formalized system here. And moreover, this extraction should not be a program in some other programming language like OCaml or Haskell or whatever, but it should be a term in your underlying logical language of the formal system you are dealing with. And in the setup that I'm going to describe, it will be a certain extension which I happen to call T+, which is a common extension of Gödel's T and Plotkin's PCF. And by that token, you have now a term in your language. You can formally prove that this extract, a certain term, indeed realizes the specification of the problem. And the specification is nothing but the formula that was proved by the proof at hand. And realizes is a technical notion in the sense of modified realizability by Kreisel, which can be formalized easily. Now I'd like to say a little more about this set of ideas, and to be a little concrete, I pick constructive analysis, and this can be dealt in many different ways, and one would be, which seems to be the first thing you think of, to do your analysis with concrete data. And that means if you have a real number, consider that, then you view that as a Cauchy sequence of rationals together with a modulus of Cauchiness. And you can carry on and consider continuous functions. This setup, uniformly continuous functions are most interesting, which are given by an approximating map that's essentially restricting of this function to the rationals and then taking as values the Cauchy sequences. And for uniformity, you have to come up with a modulus of uniform continuity. And both of these things can be organized in such a way that your continuous function is not a type 2 object which inputs real numbers and outputs real numbers, but you can get by this view by a type 1 object which has advantages. Well, this approach is of course based on this basic text of Bishop and continued by work of Douglas Bridges. And I have two little examples of what can be done and has been done in this setting. So an easy example is if you are given a set of reals S, which is, as people say, order located above. That just means if you have a rational interval and you have your set S, then you can decide by means of a Boolean whether all of S is below the right-hand side or something of S is above the left-hand side. You only have to know which of the two alternatives hold. And S has also to be inhabited and bounded, and then it's an easy construction that you can show that F has a supremum by essentially constructing a Cauchy sequence which will give you that supremum. And such a thing can be dealt with in this setting, and you can indeed extract a program that constructs a sequence. And another very easy example is the intermediate value theorem, that if you have a function that's negative on 0 and positive on 1 and satisfies certain conditions, then you can actually construct 0 of that function. Well, another possibility to go for constructive analysis from our point of view is to view data in an abstract way, which means that we can work with an axiomatic theory of reals, not concrete ones, but as we know them. And then one has to be a little careful if in your formalization you have a quantifier for all x, where x is such an abstract real, then this x could not possibly be a computational input because you have no idea what this abstract x is. The type will be a type variable here in a formal treatment. So this quantifier should be somehow non-computational. It's a concept invented by Uli Berger. So the computational content of something that you formulate in such a theory should come solely from certain predicates that you have in your language, and in particular inductively and co-inductively defined such predicates. Well, there are some examples. One is that if you have two real numbers in an interval -1, 1, then the average of the two real numbers is a real number. Again, you can prove that in a standard way with abstract reals and then extract something from this proof, which by the very fact that your reals are treated abstractly and you have a co-inductive definition of the property being in that interval, you get as a content of that proof a stream transformer. So you represent your reals by something which makes a lot of sense from a computational point of view. Another example is dealing with uniformly continuous functions and represent them by means of a certain nested inductive and co-inductive definition. This is work in progress, also based on Berger and Seisenberger, and gives a quite interesting approach to uniformly continuous functions. Well, if you want to realize these ideas, you of course have to formalize proofs, but then you have to have an underlying theory, and the theory that we work with in Munich is a certain theory of computable functionals called TCF, and I'd like to describe what the design of that theory is like. Well, first of all, the logic, the underlying logic must be constructive. That's very obvious for the purpose at hand. And this is not at all a restriction, but rather a widening of the usual standpoint, because we all know from Gödel-Jensen that classical logic can be seen as a fragment of constructive logic. I like the terminology that we have two quantifiers, a constructive existential quantifier, which is the real thing. To prove it, you have to produce something, and then a kind of a weak existential quantifier, which I write with a twiddle. And this is just an abbreviation for what you really mean, namely not for all not. And in this way, classical logic is part of your constructive setup. Well, it's certainly very important that the computational aspect of your theory and the logic is somehow intimately connected, which is done best if you allow constants in your language which are sort of representing computable functionals in finite types. You certainly need a type language to do any mathematics. And here, one point where the system I'm describing deviates from almost all others is that I think it's crucial to allow partial functionals from the outset. For instance, you certainly want to have the fixed point operator, and this thing cannot be total. And generally, you want to define a function by means of defining equations, and it's not at all clear that any such set of defining equations defines a total functional. Then, moreover, we need to know the range of our finite type functionals, and this range should not, as I am quite convinced of, should not be the set of all total functionals and also not the set of all computable functionals, but it should be rather arbitrary. And Dana Scott and Yurjashov came up with a nice model of what they call partial continuous functionals, which has very nice topological properties as well. And so in the underlying theory, the variables range over this Scott-Yurjashov model of partial continuous functionals. Now, if you have finite types, you need to know what your ground types are, and it's quite natural to pick free algebras here. For instance, natural numbers. These need not be finitary, so you also ordinals would qualify as a free algebra, for instance. Now let's look at the natural numbers. If we have partiality, it's not only 0, 1, 2, and so on, but you also should accommodate partial objects. And the question is, should your domain of natural numbers be so-called flat or non-flat? And well, you have all seen in domain theory this picture of the flat numbers. You just take the ordinary number sequence, and then below it you take a bottom element, which in many models will be the empty set, and these things the single sets of the numbers. So that's a very standard approach. But an alternative is that you view numbers as non-flat, and this is in a setting which I don't have time here to describe, which is based on Dana Scott's information systems, where you have so-called tokens, which are basic pieces of information. And for instance, this thing here, successor of unknown, of star, just means that the only thing you know about your natural number is that it starts with 2 successors, nothing else. And then you can increase your information by saying that this unknown thing is 0, and then you have a total natural number. But you can also increase it in another way by saying this unknown thing will be for something which starts with yet another successor, so you have this one. So these are tokens. This is an entailment relation in the information system terminology, and the ideals or abstract objects or points for that structure will be possibly infinite sets of tokens which are consistent in an obvious sense and also deductively closed. And in this very simple model, you just have one infinite object which is just on this, all the tokens on this diagonal. But if you have a binary successor, you have, of course, many more infinite objects. So what should we pick? Well, it's quite tempting to use the flat domains because they are so nice and simple, but there are reasons not to pick them, and since this is not so well known, I'd like to at least tell about it. In a free algebra, of course, the constructors play a crucial role, like the successor in the natural number. And, well, quite generally, every constructor generates an ideal or an abstract point in the function space. And, well, this is here in the terminology of information systems, which I don't have time to explain. So with the constructor C, you have a certain continuous functional as a set of tokens called RC, and it's defined in this way. A formal neighborhood U is mapped to constructor with some arguments, and the arguments are those which can be inferred or entailed by U. And this is a certain set of tokens, and then the corresponding function in ordinal notation would take an ideal X as an argument and put out all the tokens C and then a sequence of other tokens or star, where the X is referred to by taking any formal neighborhoods, finite, consistent subset which entails the A's. Anyway, that's a very natural construction where any constructor gives rise to a continuous map, and it turns out that in our setting with non-float domains, these constructors behave well in the sense that they correspond to injective functions with disjoint ranges, and that's certainly what you want to have from a constructor. That's why they are constructors. But both properties are false if you base yourself on flat information systems. I have a counterexample here. The reason essentially is that you can easily see that you must have monotonicity for continuous functions, and also that constructors must be strict in the flat information systems. And then these are counterexamples. So if you have a binary constructor C, if one argument is empty, then it has to put out empty. If the other argument is empty as well, and this is clearly contradiction to injectivity. The same thing holds if you have two unary constructors, C1 and C2, and you apply them to the empty sets, and the ranges of these two things will not be disjoint. So just to enable reasonable arguments, it seems mandatory to use these non-flat base domains. Well, the next step will be to look at, in some more detail, at this underlying concept of realizability for extraction. Well, what we can do is we can define a formula that a certain term T realizes another formula A. Well, A is an arbitrary formula in our language with these constants for computable functionals, and T is a term in this system T plus with Gödel-star recursion operators and fixed point operators and so on. So this formula can be just written down explicitly, and then you have the crucial soundness theorem, which says the following: if you have a formula A and a proof, call it M of A. Then, by the general theory of realizability, you know that you can extract from this proof M a certain term which is supposed to or will realize this formula A in the sense defined above. And now, since our realizing term is not in some programming language, but it is in the language of our theory, this whole formula again will be a formula in our theory, so it can be proved in the very same theory. So we will internalize a certain way of reflection here. Now, it turns out that there is one also quite neglected aspect here, that it may be necessary and at least very useful to decorate your logical connectives. And in the logic I'm using, it just implies, and for all, that is the only logical connectives, and then all the other connectives like existential and disjunction can be inductively defined. That was an observation by Per Martin-Löf. So we only have to deal with these two, and so they have a computational and a non-computational variant. I already mentioned this for all non-computational, which is crucial when you work with abstract reals. You don't want to have for all x to have computational content, so you have to take this NC here. And it's also very useful for fine-tuning. You can imagine that if you formally extract from a proof realizer, that quite often you will have garbage, and you can switch that on and off, or better off if it's garbage, by using these NC decorations. And this is a very short explanation of how it works. So if you have the computational implication, then T realizes A implies B means what Kreisel and Klini said long ago. For any x which happens to realize A, this is mapped by our function T into another realizer of B. That's a standard way of how you understand realizability of implication, or the BHK view of implication. If it is a non-computational implication, then it's similar. It says for any realizer x of A, whenever we have one of that, then this T itself, irrespective of the x, realizes B. So in that sense, this x must be there, but it doesn't play a computational role. The very same thing happens for the universal quantifier. In fact, one can think a little deeper on this decoration business, and one can in fact find a so-called in a certain sense optimal decoration of any given proof, but this is something I could tell people in private if they are interested. Now, just to give you a small example here with the existential quantifier, well, I said it's not a basic connective in this TCF setup, but it is inductively defined. Well, it happens to be a nullary predicate, which is inductively defined, a little strange, but useful. And this is a single clause of it. So this predicate holds. It has, of course, a parameter, namely A. And it holds if for all x, A implies there is an XA. So it's a standard way to introduce it. It happens to coincide with the ordinary introduction axiom for the existential. And then as any inductively defined predicate, you have a least fixed point axiom. And that intuitively sees any competitor for this predicate, call it P, which satisfies the same clause. So if you have a P which also satisfies this clause, for all x, A implies P, then this P must be larger or sit above this predicate exists XA. I write the exists XA in front and the P to the back, and it fits better to normally used notation in natural deduction. So this is how you introduce existential quantifier. Now if we have our decorations at hand, here we have a universal and here we have an implication. Both can be decorated with C or with NC, and so that leads to a whole zoo of variants of existential quantifiers. These four here, D for double, left, right, and uniform. And let's just look for the double one. It says, well, the very same thing we had before, that you use the computational arrow and C all the time. Now let's look at this one, exists right. The right means you only consider the A computationally, but the X not. So that means you have a NC for all X here and a C for the A. And then you have the corresponding elimination axiom. So these things are very handy and used a lot in practical extractions. Well, let me talk about some practical aspects of what kind of problems you encounter when you want to carry out this program. But first of all, we obviously need formalized proofs to allow machine extraction. So, I mean, there are many groups in the world, and we had a meeting today about formalized mathematics, which are interested in formalizing mathematics, but normally their goal is to just have a verification that a certain proof is indeed true. And Larry Paulson here from Cambridge once stated very plainly that in Isabelle he is not at all interested in proofs, but only in the fact that certain things are provable. Here the setup is different. Here we are really interested in proofs, not only that they exist, but then they are very useful objects to do something with them, because we want to take these proofs as data to extract some content. And of course we can also normalize them and many other things, so it's quite crucial to have the proofs around. And well, if we want to carry out this kind of reasoning with this underlying TCF theory, then it's unfortunately not possible to take a proof assistant from the shelf, because the underlying theory is quite different. And so there is no way then to build your own environment, and this is what we did in MinLog for some years. It's the so-called MinLog prover, which I will only describe very shortly. It's based on natural deduction just for implies and for all. That's all. And then the only kind of driving force in that thing is inductively and co-inductively defined predicates. Somewhat similar to Koch, which is called the calculus of inductive constructions. However, I find it very convenient to separate formulas from types. So Koch is dependently typed and formulas are types. I'm just satisfied with the analogy of formulas and types and terms and proofs, and I think this is more convenient to work in that way, but that's of course a matter of taste. Well, partial functions are first-class citizens, and this is also quite uncommon in the field of formal provers. And totality, which is certainly a crucial concept that you need, has to be defined inductively, and indeed it can be defined inductively. Then, of course, to make this thing amenable to more abstract aspects, you have to allow so-called ML polymorphisms of type and predicate variables seen as parameters, which are implicitly universally quantified but not internally. Well, there are some examples where this can be applied. There is this problem of the average of two reals, which Berger-Seisenberger treated some time ago in some papers. And this was one of the case studies we have done. So one could do an extraction from a proof dealing with such abstract reals, and this proof will involve co-induction. And the proposition is that well, any two reals in this interval -1, 1 have an average in the same interval. Well, in this Berger-Seisenberger paper, they do this also with a co-inductive proof, and then when the proof is done, they look at it and informally extract a Haskell program from this proof, which has this nice feature that it works with a stream representation of reals. So Coq, of course, has also co-induction, but the way the Coq people deal with it is that they just verify certain programs written or terms written in with a co-recursion operator, whereas here the emphasis is on extracting from proofs with co-induction. Well, Kenji Miyamoto, a PhD student in Munich, he has formalized this proof of Berger-Seisenberger and machine extracted its computational content, which is quite a nice case study which shows that such things are indeed doable. I can give a demo to some people who are interested in it. It runs on a machine. Well, I think that's essentially all. This is some papers on the subject. Thank you for your attention.
So we have time for questions or comments.
What are the prospects for translating proofs from some of these other off-the-shelf systems into the TCF framework?
Well, that in principle, if the underlying argument is an ordinary mathematical argument and the underlying notions are such that they fit, and this is not always the case. For instance, if you go to MISA, it's you have Tarski set theory, and then in other systems like type theory based systems, you only have total functionals. So you cannot, of course, we can deal with total functionals, but the system is not in the first place designed for that. But short answer to your question would be, I think it's doable, but I have doubts whether this could be automatized.
Any other questions? Let's thank the speaker again.